Hi, everyone. Thank you for joining this GIA Knowledge Session, a series of seminars on gemology fueled by our decades of research. I'm Stuart Overland, Managing Editor of Gems and Gemology. In this session, we'll recap the most recent issue of GNG. For the next hour, you'll be in the good hands of two of the very best from the GI laboratory. First up is Nicole Aline, a senior staff gemologist in colored stones. Nikki will be followed by Dr. Sally Eaton Magana, Senior Manager of Diamond Identification. And before we jump in, just a few quick housekeeping notes. Everyone attending this session will be automatically muted. If you have a question as we go along, please submit it using the Q&A feature at the bottom of your screen. There'll be a Q&A session at the end where Nicole and Sally will answer some of your questions. We'll also be sending you a recording of today's session, and in that message, you'll find a survey. As always, we would love to hear your feedback. So, let's look at the winter 2020 edition. This issue was released about a month ago, at the beginning of April 21. And what you see on the cover here are 6 pink sapphires from Madagascar. The top 3 were treated using a low temperature heat treatment process. The bottom 3 are untreated. And that low temperature heating process is the topic of our lead article, which we'll get to in just a minute. But first, a quick overview of the 3 feature articles in this issue from our non-GI authors. The first one comes to us from Dr. Carl Schmetzer with a fascinating look at rose-cut colored stones from the 17th century. These rose-cut stones embellished rare artifacts that once belonged to the archbishops and prince-electors of Cologne and Trier. And in this article, you'll see corundum, peridot, garnet, and quartz with a variety of rose-cut patterns. The next article is on blue amber, which shows this very strong blue fluorescence under UV light. Ziqing Zhang, Andy Shen, and co-authors at the China University of Geosciences in Wuhan provide a means of separating blue amber from the 3 main localities. Those are the Dominican Republic, Myanmar, and Mexico. And they were able to separate the geographic origin of these blue ambers using a combination of observation, UV-Vis and IR testing, and excitation emission mapping. And finally, Duan Vu, Shakapan Sudarat, and co-authors investigate mineral inclusions in basaltic sapphire from southern Vietnam, which you see in these 2 rings. The authors analyzed the chemistry of these inclusions to better understand the formation model of the sapphires in relation to the basaltic volcanism of the locality. And without any further ado, we'll get started on colored stones and pearls, brought to you by Nicole Aline. Here's Nicole.
Hi. So heat treatment has been used to improve the color and/or clarity of corundum for more than 1,000 years. Various parameters such as temperature heating and cooling time and oxidizing or reducing an atmosphere will affect the final color. Now, the border between high temperature and low temperature heat treatment is roughly 1200 to 1350 degrees Celsius. Heating at such high temperature will damage most inclusions in corundum and is often detectable by trained gemologists. But when heating corundum at much lower temperatures, it will only subtly affect the internal characteristics and inclusions, making the treatment more of a challenge to detect without advanced instrumentation. This article discusses the effect that these low temperature heat treatments have on inclusions and the FTI, the infrared spectroscopy spectra for pink sapphires from Madagascar. So pictured here are 11 samples reportedly from Ilakaka, Madagascar, and show before and after heat treatment. They ranged in sizes from 0.41 carats to 2.15 carats and are all polished with at least 2 windows for data collection. 9 of the 11 samples were purchased directly from the miner, but not at the mine. And if you are familiar with GIA's colored stone reference collection, this classifies them as C-type samples. 1 was acquired from a trader in the market and is classified as an E-type sample. And 1 was purchased from miners at a washing site, which defines it as a B-type sample. These 11 stones were subjected to heat treatment in air at 800 degrees Celsius for 160 minutes. So prior to heat treatment, these samples were purplish pink. And following that heat treatment, again at 800 degrees for 160 minutes, the blue color component showed a significant reduction, leaving the stones a more pure pink. This observation has also been documented in heated rubies from Mozambique. So when observing these FTIR spectra of the rubies from Mozambique that were subjected to heat treatment, stones had a single 3309 peak that you can see right here in the blue spectrum. And then as it was heated, a 3309 series developed, which is that 3309 peak with a 3232 and or a 3185 peak. Now in this study, all the samples showed a decrease in their 3309 peak after being heated, and 9 of the 11 developed a 3232 peak, with no 3185 peak being observed. Now, it is worth to note that these samples some of them were sort of small, which results in a shorter path length of light through these stones. And so the series is easier to collect when you do have a larger stone to run the spectra through. Now, the authors also collected FTIR spectra on 250 additional unheated pink sapphires that were also reportedly from Madagascar. And 130 of these stones showed a single peak at 3309, with none showing a 3309 series. Now, internally, pink sapphires from Madagascar commonly contain zircon crystals that have like a rice grain shape and occur in clusters or as single crystals. They also contain needles, particles, thin films, and can have crystals of mica and monazite. And so during the low temperature heat treatment, these inclusions show no change when heated at that 800 degrees Celsius for 160 minutes. Some epigenetic iron staining did get darker to the presence of oxidation. However, when looking at monazite crystals, they did actually observe that they went from this nice orange brown color that you can see in box A to near colorless. So pictured here, you can see the range of that monazite going from that nice orange brown to colorless. So pictured in box A is that pre-heat treatment, and it was identified using Raman spectroscopy. And then if you look at that box D, that's the monazite at 600 degrees. So it's already starting to become colorless. And then once you reach that box F, which is now reaching about 1000 degrees, so you're coming up to that higher heat treatment, you're developing a very noticeable tension crack. So during this low temperature heat treatment, it still remains a challenge since some inclusions such as zircons, needles, and particles are often not affected by low temperature heat treatment. And since we have seen that presence of the 3232 peak with a 3309 peak in that FTIR spectrum be related to heat treatment, and while this peak is only found in heated stones, the absence of it is still not an indicator that your stone was unheated, but it definitely aids in that call. And then again, another possible indicator is in this heat treatment call is that observation of colorless monazite crystals that again have that typical orange brown color fading to that near colorless. So the presence of a near colorless monazite inclusion does suggest that this stone was subjected to heat treatment. So this, moving now to the lab notes section. So this section is dedicated to interesting things we see in the lab, things the trade should be aware of, such as new treatments or stones that we find that are just unusual and atypical. So seen here are two bluish green prisms weighing 1.91 and 1.92 carats, and they were examined at the Carlsbad laboratory. And they contain these eye visible clusters of reflective brown metallic crystals. From afar, these stones seem to resemble peributermoline with copper inclusions. However, a single refractive index of 1.5 and a hydrostatic specific gravity of 2.43 on both crystals immediately ruled out tourmaline, as tourmaline is doubly refractive, and its refractive index is 1.62 to 1.64 and has a specific gravity of 3 to 3.1. So under microscopic examination, things seem to be just slightly off a little bit on these stones. With the aid of the fiber optic light, both crystals showed trapped gas bubbles, a flow structure, and a distinct boundary where two types of glass, the one with the geometric copper crystals with that yellow body color, and then that host bluish green crystal, you can see where they were fused together. Advanced testing was done to confirm that these were man-made glass, as well as the presence of copper from those that encapsulated goldstone glass. What was interesting, though, is that during the same time that these manufactured products were being observed, a natural copper-bearing tourmaline from Brazil was being examined in the same lab, again at the same time. So this natural stone has rare dendritic copper inclusions that you can see in the photo on the right, that these two pieces of manufactured glass were trying to mimic. And it's very unusual to see man-made glass cut to imitate its rough counterpart, but it's also unusual to see that natural rare counterpart in the lab at the same time. So very cool to see. So seen here is a 28.16 karat polished rough dark green common opal that was submitted to the GI Carlsbad Laboratory for identification. It had a refractive index of 1.45 and with a specific gravity of 2.07. And there was no play of color observed, again, categorizing as that common opal. So internally, this opal housed these several small, well-formed black opaque octahedral inclusions with some yellow staining. And with the use of advanced testing, Raman and laser ablation inductively coupled plasma mass spectroscopy, which I will call ICP from the rest of these presentations, the inclusions are identified to be chromite, with chromium being that coloring agent for this common opal. So here we see a 3.93 carat 10 colored purplish pink hexagonal modified cut sapphire submitted to the Carlsbad Laboratory for identification origin service. And it's photographed next to a rough research stone. So this stone had a refractive index of 1.761 to 69 and a specific gravity of 3.99, which is consistent with corundum. So microscopic examination revealed intact crystals with these decrepitation halos seen in the photomicrograph on the left, and then dense bands of exsolution silk interspersed with finer bands of silk seen on the right, as well as reflective films, fluid films showing no sign, and all these showing no signs that the sapphire was subjected to heat treatment. So advanced testing with that ICP-MS was used to obtain the stone's trace element chemistry, which concluded to be consistent with Montana sapphires from the GI Colored Stone Reference Collection. So the internal characteristics were all consistent with Montana sapphires, specifically from secondary Montana deposit, which include Rock Creek, Missouri Creek, and Dry Cottonwood Creek. And so this 3.93 karat purplish pink sapphire is reported to be from Rock Creek deposit, which is known to produce these sapphires of unique colors and very excellent clarity. So the Bangkok Laboratory analyzed a 0.52 karat blue flux sapphire. So it had standard gemological properties, including refractive index and specific gravity that were all consistent with corundum. And then microscopic examination of the stones revealed platinum and platinum inclusions in a variety of shapes, as you can see in the photomicrograph on the right, which is typical of Chatham laboratory grown sapphires. However, the most interesting feature of this stone was its UV-Vis near IR spectrum. And so the spectrum had this, the usual 377, 388, and 450 peak, which are related to iron. And then an iron 2+, titanium 4+ broadband around 580. And that is responsible for that blue color that you see in the stone. But additionally featured is this unexpected broad band around 800 nanometers. And this band is typical for basalt-related natural blue sapphires and can be found in some heated metamorphic blue sapphires as well. However, it has not been reported in a blue lab-grown sapphire, either of flame fusion or flux grown. So next we're going to talk, we're going to look at the microworld section, and this is an in-depth look at the hidden worlds of gem inclusions through photomicrography. So here we have a 5.33 karat red pyrope garnet, which is reportedly to be from Madagascar. Now this author picked this rough for an eye visible blue apatite inclusion just below the rough surface. They then prepped and cut the stone to orientate that blue apatite crystal to be on full display through the table of the finished cut, cornered, mixed cut, as you can see in this photo. So with microscopic examination in the aid of a fiber optic light, that blue euhedral crystal shows that it was surrounded by these elongated intersecting iridescent needles. And this stone is just a really perfect example of cutters showing off inclusions rather than hiding them. So available in the market since 1970, the John Saul mines in Kenya have produced large quantities of rubies of very fine color. The rubies themselves are mined from a vein that intrudes an ultra basic body, which is basically an igneous rock with very low silica content, and it's intruding that country rock. So the rubies have an inclusion scene that consists of bands of dense clouds of particles associated with iridescent short needles, which we see in this photomicrograph. Their inclusion suite also has these negative crystals surrounded by iridescent thin films pictured here. And these inclusions have been documented in John Saul rubies, are familiar to the inclusions rubies with marble-hosted origins such as Mogok. And it just shows that similar inclusion stains can form in very different geological environments and that the internal world of gemstones is not always an inclusive indicator for geographic origin. So rubies from Mongshu typically have distinct zoning with dark violet cores, a cloudy appearance, and multiple fractures when they are mined out of the ground. So as a result, most of these stones from this deposit are heat treated at moderate temperatures, using flux to repair these fractures, improve their clarity, and remove that unwanted blue color. So the Bangkok laboratory recently examined a 0.79 carat sugarloaf cabochon ruby. Gemological observations with chemical analysis indicated that the origin of the ruby to be Mongshu, and then while observing the stone under microscopic examination with a combination of dark field and fiber optic illumination, an open fissure with a snowflake-like pattern, as you can see here, from that flux residue was documented. And so this pattern is formed by the crystallization or devitrification of that glassy flux residue. And this partially healed fissure resembling these beautiful snowflakes is the first such feature the author has encountered in a flux heated ruby. So rutile is a titanium dioxide and is a mineral that generally occurs in corundum as silk, dust-like particles, or macroscopic crystal inclusions. So the rutile crystals can have an orange to dark, like a deep red-brown coloration, and can be rounded or euhedral in shape, as you can see in this photomicrograph. And so the author recently examined a 4.24 carat faceted blue sapphire from Afghanistan. And the stone contained dusty flake-like inclusions, naturally healed fractures, twinning, colorless apatite crystals, and then this very unusual long prismatic orange crystal that was identified as rutile. And this rutile crystal shape is just not typical for blue sapphires. So while examining a dyed and polymer impregnated jadeite jade bangle bracelet classified as sea jade in the trade, this author noted a well-formed transparent brownish crystal inclusion. Raman analysis of the doubly terminated tetragonal prism revealed it to be a high zircon with little to no damage occurring to its physical and optical properties from metamictization. Although interstitial zircon grains are not uncommon in jadeite, euhedral crystal is rarely observed, and it is very surprising considering the various treatments that this host jadeite has undergone. So the quarterly crystal for the G&G Winter 2020 issue is a 26.16 carat transparent light blue hexagonal prism of aquamarine beryl that is terminated with a flat pinacoid at the top, and it was reported to be from the Shigar Valley in Pakistan. So microscopic examination revealed numerous saturated orange syngenetic garnet crystals near the base of this aquamarine. With the aid of Raman analysis, the garnets were identified as spessartine, and then with garnet inclusions in beryl being rare, these euhedral crystals give insight into that pegmatic origin of this aquamarine and its locality. So next we have Gem News International, and this is just global coverage of gem sources or new localities, notable new gem material, and recent industry developments and current events that are going on. So meteorites, which are natural objects from interplanetary space, are classified into three broad categories: stone, iron, and stony iron. With iron in this, with the iron and stony groups popular with the gem and jewelry industry. Iron meteorites, when acid is applied to a polished surface, it starts to dissolve parts of the stone structure, creating an intricate coarse pattern known as Widmanstätten structure, with no two structures being alike. So pictured here, we see two rhodium plated iron meteorites, a 28.53 carat mounted pendant and a 36.69 carat loose slab. They were acquired by one of the authors during the Tucson Gem and Mineral Show in 2020. With the pieces having an abnormally high metallic luster and bright white color compared to a typical polished and etched meteorite, two pieces were suspected to be an imitation of iron meteorite. So chemical analysis of the elements using the LAICPMS revealed that the two pieces were authentic etched iron meteorites that were plated with metals including nickel, copper, and rhodium. So displayed in the figure is a chemistry comparison of the pendant versus non-plated iron meteorite. So along that y-axis, so top to bottom, is the concentration of these elements detected, with that x-axis representing the depth of that LAICPMS as it drilled into the stone. So for the pendant at the surface, there are high concentrations. So you can see, try to highlight it for you. So right over here, there are these high concentrations of nickel, copper, and rhodium, and then they taper out to just iron and nickel, which are the only two elements present in that non-plated iron meteorite seen in that profile below. So iron meteorites are prone to rusting due to their high iron content, and even as slight humidity within air causes rapid corrosion. So rhodium is categorized by high stability, good resistance to corrosion, and a high melting point. So rhodium plating offers an attractive luster and color to the surface, with this essential function in this instant to prevent the rusting of that meteorite. So the World Pearl Congress was held in November of 2020 in the town of Shanxiahu, a division of the Chinese city of Jiuji, known as China's pearls capital. So the town of Shanxiahu produces nearly 80% of China's pearls and is currently home to more than 2,500 pearl companies. So the event consisted of a series of activities, presentations, and exhibitions focused on pearls. So more than 400 attendees who live in China and represent a number of professions and industries attended this meeting in person, while several international and domestic speakers delivered a series of talks via pre-recorded videos. GA consultant Nicholas Sturman presented via video on freshwater pearls from a laboratory perspective. The World Freshwater Pearl Museum was also unveiled in Jiuji, China, with exhibitions on the rich history of the pearl culturing in China, pearl cultivating and processing techniques, and variety of freshwater pearl and pearl jewelry. And several sources have mentioned that the global pandemic caused little disruption to the production of freshwater cultured pearls. The harvest usually takes place at the end of the year, and the government's fast control helped minimize that impact. So the export of freshwater cultured pearls have been significantly affected though, and the dealers are trying to boost domestic sales with more emphasis on a strong online presence. Among different sale methods, live streaming has been become an even more popular way to sell pearl jewelry in China, and it is reported that from January to November of 2020, online sales of pearls in Jiuji had a year-over-year increase of 18.5%. And now here's Sally with diamonds.
Thank you, Nikki, and glad to be talking with everyone today about the diamonds that were profiled in the last issue of Gems and Gemology. The first diamond we'll talk about is this 1.5 carat round brilliant. It has fancy intense green yellow color. Was studied by Brittany Roy and Virginia Schwartz. The diamond was determined as a type 1AB, and it had distinct evidence in its spectroscopy of both high pressure, high temperature, and artificial irradiation. Under magnification, the stone showed strong green luminescence by fiber optic lighting. The next slide shows how it looked under the microscope under diffuse lighting. The stone had both yellow and brown graining, as well as some unusual blue graining. Now, graining is related to distortion in the diamond's lattice structure, such as plastic deformation that occurred while the diamond was in the earth. Colored graining can be observed when this plastic deformation occurs along with nitrogen defects, typically. That's the typical case, but this diamond had the blue graining, which seems to tell a different story. The gemologist reasoned that the radiation damage was the most likely cause of this blue graining. Before HPHT treatment, this stone had a brown color, which with the treatment transitioned to a yellow, as well as the green luminescence, which added the greenish component. After laboratory radiation, the authors surmised that vacancies were created in higher concentrations within low nitrogen regions to create the zones of blue color. This next figure shows a diamond view image showing both strongly fluorescing blue areas and inert areas that are indicated by the red arrow. Those inert areas correspond with lower nitrogen and the observations of blue graining. Now, in the vast majority of natural diamonds, they have nitrogen-related defects that typically absorb in the blue, thus causing the transmission window due to irradiation to shift to the green. However, in diamonds that have very low to no nitrogen, they can be irradiated to a blue color. Or in the case of this diamond, only those portions that had a very low nitrogen were irradiated to blue, thus causing that blue graining. This stone shows that interesting effects can be seen due to local differences in impurity concentrations, such as the low nitrogen, and how these can be affected differently by treatment. The next stone I'm going to talk about is this irradiated blue diamond. This diamond is 0.53 carats and was recently submitted to the New York laboratory, and it proved to have an interesting past. Its color grade is fancy light blue, which ultimately approved to Paul Johnson and Surjit Wong that it was due to laboratory radiation. This next slide shows that when it was mapped at nitrogen temperature with a photoluminescence microscope, this GR1 radiation is concentrated on one side of the table facet and on the crown of the diamond. The red areas that are the false color red that's near the bottom of your screen. This GR1 this radiation damage, along with the spectroscopy and the gemological features, allowed the authors to confidently determine that this diamond had been artificially irradiated to create the blue color. Nevertheless, it contained gemological features that were consistent with natural pink type 1A diamonds. This included very strong graining and glide planes that had a pink color. An internal GIA search of previous records revealed that this had a prior report with fancy light pinkish purple color grade. On the next slide, it shows a comparison of the before and after images. Generally, stones that are selected for treatment are those that are typically deemed as having an undesirable color. However, that would definitely not be my opinion for this natural pink diamond on the left. Nevertheless, this was selected for treatment. The next slide shows visible near-IR absorption spectra collected from this irradiated diamond and compares it with the original natural diamond. The natural diamond shows a broad band at about 550 nanometers, which is typical for this type of diamond, and the pink color is due to plastic deformation that generally occurs deep in the earth. After irradiation, we see the 550 nanometer band and the addition of the GR1 peak and its side bands. In the absorption spectrum for the blue treated diamond, the combined effect of the 550 nanometer band absorption along with the GR1 absorption and its sideband causes this near violet color. And I really think this is a great example of color engineering, and I can only suppose that it was intended to be an interesting experiment by the treater to gauge what might be possible when a natural diamond that is not normally chosen for treatment is subjected to laboratory radiation. And it certainly results in a diamond that is generally not seen in nature and not often attempted within the trade. The next diamond that I will be discussing was submitted to the laboratory here in Carlsbad, and my colleagues, Dr. Aaron Palke and Dr. Mike Breeding, were able to examine what I like to nickname a born in the USA diamond. The Cushing cut is a 1.16 carat and near colorless. It was submitted for a grading report, and it also has a certificate from Creator of Diamonds State Park in Arkansas, USA, which indicated that it had been cut from a rough of 2.73 carats. It was mined in July 2020 by William Dempsey. The diamond was also reported that it was cut and polished in North Dakota. At 2.73 carats, the rough was definitely quite large for an Arkansas diamond, as most diamonds found in that state park come in well under 1 carat. The diamond turned out to be fairly clean and with no crystals. However, there was a feather along the crown that gave it an SI1 clarity. But because it had no crystal inclusions, they were not able to perform any additional analysis that might have more about its geological history for that stone or for the diamond deposit in Arkansas. Surprisingly, IR spectroscopy revealed that this stone is a type 2A diamond with no measurable nitrogen impurities. Now, we've known that only about 1% to 2% of colorless to near colorless diamonds are type 2A. So definitely discovering a type 2A gem diamond is rare enough, but for those of us who live in the United States, uncovering one from here where few diamonds occur was quite interesting indeed. The next diamond we're going to talk about is a laboratory grown CVD. And in fact, it's the largest one that has been submitted to GIA. This was recently submitted to Carlsbad, and it was analyzed by Garrett Michelini and myself. This stone is 7.07 carats with VS2 clarity and M color. It was undisclosed as CVD, but our normal stone flow and procedures correctly identified this diamond's origin. Now, the next slide shows a diamond view image, indicates several diagnostic features. It shows striations, which are the results of CVD diamonds growing up atom by atom. And if you cut across those, then it can resemble a staircase. The diamond view image also indicates a stop-start growth event. Both of these features help confirm the CVD growth origin. Additionally, the fluorescence color, green, shows that this CVD grown diamond was subsequently HPHT treated. This treatment is generally intended to reduce the brown coloration present in many as-grown CVD laboratory-grown diamonds. Now, while 7 carats is large for a CVD, and it's the largest one seen at GIA, it is not the largest one reported. To my knowledge, the current record holder is a 12.75 carat round brilliant that was reported in the trade press back in November of 2020. Now, while we're on the topic of CVD diamonds, that's also this next stone. This now fluorescence is a really important part of diamond analysis. And so we're going to showcase some fluorescence images that we see here in this. It's a rough CVD block that was grown here at GIA. Its total weight is 5.8 carats. Now, with fluorescence, each color can provide clues to the growth chemistry, possible post-growth treatment, as we saw with the previous diamond, and defects that formed along the way. Now, gemologists use these data along with spectroscopy and other gemological features to determine a diamond's origin and treatment history. So researchers at GIA grew this CVD block over several growth runs to help gain a better understanding of CVD lab-grown diamonds. And while it is helpful scientifically, the author of this note, Stephanie Prasad, also recognized that it could be appreciated for its aesthetic beauty as well. The fluorescence features that we see on the right were collected with the Diamond View microscope. And in this experimental CVD block, it resembles a landscape of trees reflecting into a lake during a beautiful sunset. That's how Stephanie described it in the micro world, and I definitely agree with that. You can see in normal lighting that this CVD diamond has many internal defects, such as obvious graphite inclusions and a pronounced growth layer interface at the middle. However, all these imperfections contribute to the beautiful fluorescence results that we see on the right. And I like this example just because it helps to remind us that intriguing and beautiful images can come in the unlikeliest of places, even in this experimental, defect-ridden block diamond grown in a laboratory. So we're going to go from laboratory-grown diamonds back to the natural diamond world, and we're going to I'm going to attempt to summarize a regular series about diamond geology written by two great diamond geologists, Dr. Karen Smith and Dr. Steve Shirey. Now, I know the font is small on this chart, but this contains such a wealth of information. It shows a summary of the ages for all diamond mines that have provided enough data for them to be included. This diagram summarizes all of the known diamond growth events through time. One thing we immediately see from this chart is that diamonds have formed throughout nearly all of Earth's history and are likely forming today beneath our feet. Diamond mines typically have diamonds with ages covering a vast span of time and may have both eclogitic and peridotitic diamonds. I want to mention that this plot represents a huge amount of work from the scientists involved and really helps us learn so much more about diamond ages across the millennia. Researching diamond formation has been very important for geologists, as diamond formation often coincides with tectonic processes. It has also become an important component of researching continental changes and carbon cycling between the crust and the mantle over the last 3.5 billion years. Now, the two main types of diamonds identified on this chart are peridotite and eclogite. So what are those? These are two types of rocks that are found in the lithospheric mantle. Peridotite is the major rock type found in the mantle. Eclogites, in contrast, are about less than 1% of the rock within the lithospheric mantle. So the oldest known diamonds are the 3.5 billion years old diamonds from the Diavik and Akati mines. This global compilation of diamond ages from all the studies shows that prior to 3.1 billion years ago, only peridotitic diamonds formed, whereas diamonds younger than 3 billion, most of those are eclogitic. This shift could have been caused when subduction and continental collision created the movement of eclogite and diamond forming fluids into the mantle lithosphere. This next figure shows a schematic of the Argyle mine in Australia. The Argyle mine is well known for its pink and red diamonds, and during its mining life that spanned more than 30 years, it provided a high output of diamonds. It is also probably the best example of a diamond deposit related to collisional mountain building. Prior researchers showed that subduction along the Kimberley Craton edge helped create the Argyle diamond deposit, which is illustrated by that downward arrow within the figure, within the green colored section. It also shows several of the temperatures generally experienced at various depths and the resulting diamond formation. The eclogitic diamonds formed shortly after continental collision at about 1.6 billion years ago. And after these were formed, these diamonds remained in the high temperature, high deformation region. The region is comparatively close to the convecting mantle, and this likely provided the necessary conditions to impart the strain to some of the diamonds that helped contribute to their pink and brown colors. Now, the next figure shows an illustration of the South America lithosphere currently under the Andes Mountains and is based on seismic data. Diamonds are still likely forming right now, although there really is no way to prove that, as we don't have access to those diamonds. Based on the relationship between diamonds and global plate tectonics, the authors could make a few predictions about where diamonds currently might be forming. Most of the Earth's mantle is at the right pressure and temperature conditions for diamond formation. However, in order to find the diamonds currently being formed, we'll have to wait for a kimberlite or lamproite eruption to bring those diamonds to the surface. However, that last kimberlite eruption was more than 10,000 years ago, so we'll probably be having to wait a long time. And that concludes my portion of presenting the diamonds, and we are ready to take some questions.
All right, thank you, Sally and Nicole. We've just covered 110 pages of G&G content, and have some questions for both of you now. So I'd like to start with Nicole and give Sally a chance to catch her breath. So Nicole, You touched on GIA's sample classification scheme. Could you tell us more about that, please?
Yeah, so when our field gemologists go out into the field and collect those samples that we use here, as you saw in the secondary Montana Sapphire lab note, when they collect the samples, they want to make sure that they are documenting them correctly, and also want to make sure that when they document them, they're giving them a sample type. And so they're giving them a type based off of how they collect them. And so there is a couple different samples that I've touched on already. So like that B type when it was collected from a miner at the mining site, but the GIA field gemologists did not collect it themselves. If the field gemologists collected themselves, that would be the top grade. That would be A type sample. That means that the field gemologist mined it directly from that mine. And so it goes, so then we got the B type, then we have C type. So they're collecting it at the mine, but they didn't witness the mining. We have D type, which is it's collected from the miner, but not at the mine. Then we go to E type, which is it's purchased from a dealer at a local market that's close to the mine. And then after that, we have F type, which is collected in international markets. So you can see there's a wide range, and it just helps us be more precise to where that actual stone came from and more conclusive on the origin of that stone. And then we end it with Z type, which there's no origin information on that sample at all.
Great, thank you. And Nicole, could you also explain further UV-Vis spectroscopy and its importance with blue sapphires, please?
Yeah, so the UV-Vis that we saw with that flux-grown sapphire was typical of that magmatic origin of a blue sapphire. And so we use UV-Vis in the lab to help us assist with our calls to narrowing down that blue sapphire for origin for that metamorphic or that magmatic. So that metamorphic origin, we're looking at like Madagascar, Burma, Sri Lanka, and that magmatic, we're looking at more of Australia, Ethiopia. And so when we collect that UV-Vis spectra, we're looking at what's that coloring agent of that stone. So our metamorphic has that lower iron content, and there's actually less amount of peaks and bands in our UV-Vis that we're collecting. So when we're analyzing a spectra that's run for a blue sapphire, if there's that single broad band at 580, which is that it's an intervalence charge transfer. So we're looking at the transfer of two metal sites, that iron and titanium, in a single peak at 388, and again related to iron. That's indicating that that stone is from that lower iron content origin. But when it has more of those peaks that we saw in that flux grown, so that 377, 388, 450, and then that broader band at 880, that's indicating that it's from a higher iron origin. So again, we're looking at that Australia, more of that magmatic origin locality. So UV-Vis spectrum is super helpful when we're looking at when we're looking for that assistance on our geographic origin call here in the lab.
All right, and let's have some inclusion talk here. Can you tell us how do you get rutile as both silk and crystals inside corundum?
So when you're looking at rutile and corundum, they can be protogenetic, meaning that they prior to the corundum. Syngenetic, they formed with the corundum, and epigenetic, so they formed after that corundum was grown. So that rutile, that elongated rutile crystal that we saw in that Afghanistan corundum is probably syngenetic. And so you saw that because it was well-formed crystal. So as that corundum was growing, that titanium oxide was present in an equilibrium to create a rutile crystal and not corundum in that space. So as that corundum was growing, that rutile was growing as well as a syngenetic crystal. And then we you can see like exsolution rutile silk, which is more of like an epigenetic. And so after that corundum was done growing, and it's still in the ground, so it's still under at higher temperature, higher pressure than at the ground level. I'm sorry, after it reached the surface and is plucked from the ground, that titanium oxide is exsolving out of that corundum, and it's being created into silk. So there's just different paths that titanium oxide in that form of silk can and that crystal can form, creating different inclusions within your sapphire and ruby. All
right, one more question on colored stones for you, Nikki. You walked us through UV-Vis a moment ago. LAIC PMS, that's a technique it shows up in G&G all the time now. advanced technique for chemical analysis. Most people never get a chance to work with LAICPMS. So could you just explain a little bit about it and why it's so important to the laboratory?
Yes. So LAICPMS, or ICP, the shorthand, or the longhand version, the laser ablation inductively coupled plasma mass spectroscopy, which is the much longer version, is a highly sensitive device that we use here to collect qualitative data. So we're looking at the quality of elements within a stone. And so it is destructive because it does collect a very small sample, but the holes that are left behind are usually microscopic. And we use it to collect chemical analysis. And it's very useful because we can collect chemical analysis in very small amounts, so parts per million atoms, and it's rather quick and it's very direct. And we can use it on both loose and mounted gemstone, which is very useful here in the laboratory. And it's very precise because the measurements we can collect around a wide range of elements and even on like very ultra trace amounts. And so because it does that, it's very precise. We can do it on a wide range of elements. It's super helpful. And we use it all the time here every day to help detect treatments such as beryllium diffusion. It provides us the data for geographic origin determinations, and that it can also aid in those natural or synthetic hulls for a wide range of stones. So because that's, again, quick, precise, we can look at many different elements rather quickly. It's a very useful device here in the lab.
Great. Thank you, Nicole. And Sally, let's have a little lightning round with some questions for you. First, what causes the GR1 band?
That is due to irradiation, either in a laboratory or within the earth. When it's within the earth, it's when a stone comes into close contact with radioactive minerals or radioactive fluids. And in a laboratory, it can be done by a variety of ways. Typically today, it's done by exposure to electron beams. But what that does is the radiation causes the carbon to be knocked out of its home position, and it creates a vacancy where there's a lack of a carbon atom where there should typically be one within the diamond lattice. And that creates what we call the GR1 defect. That creates an absorption at 741 nanometers within the red, but it also creates a sideband that goes from the red into the orange and the yellow, which helps create a transmission window within the green to the blue portions of the visible spectrum.
Great, thank you. And let's see here. Can you briefly explain fibrous diamonds for us?
Oh, sure. Those typically are not gem quality. So we don't discuss those too much within for gem diamonds, in reference to gem diamonds, but they have a lot of inclusions, fluid inclusions and other elements. And so that can help us geologically to determine more about what's happening deep in the earth. So that would be a brief description of fibrous diamonds.
Okay, a lot of interest in CVD, synthetic diamonds, CVD
Sure.
lab-grown diamonds. Can you tell us which country or company has created the largest to date?
Oh, now the one that I mentioned that was in the trade press, but we didn't see a GIA, that was 12.75 carats. And that is reportedly from a Chinese manufacturer called Shanghai Zhengxi. And so that's, but I didn't get to examine the diamond, and that did not come here to GIA, but that's what was reported about that 12.75 carat CVD.
Okay, and the CVDs are getting larger and larger. What's the limiting factor in size for them, and how large can they go?
Well, yeah. My answer now would be different than what it was 10 years ago, which would be different than what it was 20 years ago. The goalpost keeps changing. So right now I can't really give an upper limit, although I think it'll definitely be lower than what we can grow for HPHT diamonds. HPHT grown rough have passed the 100 carat mark. That's for rough, that's not for faceted, but so a couple of HPHT grown manufacturers have passed that 100 carat mark. I don't know when or if that's possible for CVD grown diamonds. A couple of the limiting factors for CVD is with extended growth, you start to go from single crystal to say polycrystalline to non-diamond crystal growth. And so they have to do a variety of methods to try to prevent that progression from single crystal to polycrystalline. They can take the diamond out of the reactor, clean it off, and then put it back in. They can try to flip it and grow both grow up and then turn it over and then grow again, or also grow out on the sides. So there's a variety of methods to try to increase the overall carat weight. But for right now, I would put the limit at around, say, for the rough, probably about 20 to 30 carats.
Okay. All right. And then switching over to diamonds mined from the earth, do we know do we know the age of the oldest known diamond?
I believe the oldest known diamonds, I believe, are about 3.5 billion years old, and they come from the Diavik and Ekati mines in Canada. Now that's the diamonds that have been able to be analyzed. They have to look for inclusions that they can do the carbon dating on, and so they may not. There may be an older diamond out there that they weren't able to do that dating on, but the oldest diamonds that have been dated are from about that time period.
Okay, and I think we have time for one more question for you, Sally. It's really cool when researchers get to work on museum pieces like the one like the 17th century artifacts from Carl Schmetzer's article in this issue. And Sally, I know you've had some experience with that. Can you tell us a little bit about it?
That was definitely a great time for me. That was actually how I got into gem diamonds. Before that, I'd been growing laboratory grown CVD laboratory grown diamonds for engineering applications. But then I got to do a collaboration with the Smithsonian Museum, looking at the phosphorescence of the Hope diamond and other blue diamonds in their collection. And I definitely got bit by the gem bug with that experience. But I really love getting to be in the back rooms of the Smithsonian. There are some special circumstances when you are testing within a museum environment. You don't have access maybe to the same sorts of equipment that you have within a gem lab. Also, it's usually just the scientists that are looking at it. If you want to get a color grade, then we would need to have like experienced color graders to make that assessment. And it was just a great experience to get to be part of that. But yeah, there's definitely concerns due to the size of the stones, the value of the stones. We didn't put any of those in liquid nitrogen. Although that's a common practice here at GIA, we did not put any of the stones in liquid nitrogen there.
Understandable. Okay, so that will wrap up our Q&A for today's session. But before we go, I'd like to remind everyone that every issue of GNG, including the latest one, can be downloaded for free by visiting our homepage. That's www.gia.edu/gems-gemology. You can also purchase the print edition of the journal as well as GNG charts by going to the GIA store. That one's easy, store.gia.edu. And if you haven't already, join the GNG Facebook group. It's a vibrant community of gem lovers, 15,000 strong, and with a steady stream of fresh content all the time. And finally, please be sure to join us 2 weeks from today on May 27th for the next GIA Knowledge session. Dr. Evan Smith will be discussing identifying mineral inclusions in diamond, and there's no one better to talk about that topic than Evan. So thank you once again, Nicole and Sally. And on behalf of everyone at GIA, thank you for watching today.
Bye.
Bye.